Anyway, I'm Jordan. I am the Director of Energy Storage Development for Spider9, and we create controls and full systems to make energy storage smarter and more reliable and profitable. So we are a startup company, but we've actually been around for 4 years. We are established in Northville, Michigan as a spin-out from the University of Michigan. We have some patents and trade secrets that we've taken from a incubator there. And so just to kind of sum up what we do, through our software and our intelligent design, we've come up with a way to make energy more secure and provide independence. So traditionally with energy storage, most of our competitors, we found some problems with them. A lot of times you'll find issues with the reliability, with the safety. For instance, if you're from Hawaii or have heard of the Kahuku wind farm, they used to have an energy storage facility that actually caught on fire and propagated and burned down pretty much the whole facility. And also they might not work when you want them to, and typically only have one kind of function for a specific set of batteries. So basically it's kind of like your car battery. It starts your car, that's all it does. Or it's a battery just to provide backup power, like your UPS you plug into your wall for your computer. So we like to call them one-trick ponies. They do one thing and they're great at it. So what we did was develop OSE. And what it does is it takes one bank of batteries and you can do multiple things with it, while all of the time making it more reliable, making it as safe as possible, and providing it options to change in the future if you're going to use different battery chemistries or if you want to do different things with your battery system. So like I said at the beginning, we don't just make the software, we actually make full solutions. We're at a TRL 8 right now. We are getting more customer traction in the mainland, so hopefully we'll be a 9 by the end of the year. So kind of to sum up what our software does, you can divide the functions into two different categories. One is actually like a battery management system, so BMS is the acronym for that. So that's going to make the battery cells last as long as possible and get the most energy out of them for 20 years. On the other side, we have a suite of applications that the batteries can actually do. So that would be like site control for a microgrid environment. That would also be providing backup power or overall grid support. So this is a little glimpse at what actually our OSE looks like from the user interface. It basically provides a transparent look into what your batteries are exactly doing. It actually goes down to every single cell in the system. So instead of just treating a bunch of batteries as one big block or one big container or one rack, it's actually treating them on the individual cell basis. And so this can be a part of a controls box, or it can be part of the full solution. And so we've taken this software and our hardware design, and we provide all scales of storage capacity. So whether you want something kind of smaller for maybe just a tent, and all these tents on a base are connected together, all these little small ones can communicate to each other. Or you can go up to a container size to power an entire camp. So basically some of the major advantages of our system compared to anything else you're going to see out there is you can use just the one system to do whatever you want basically with it. You can get multiple value streams from it, from backup power, frequency regulation, microgrid management, the list goes on. You're also future-proofing your system. So right now there's a lot of new companies coming out with different kind of chemistries or different kind of methodologies of how to manage batteries or how to store power. The software does not care at what kind of chemistry you're using, or if you're using multiple types of batteries, or if you have old batteries and new batteries or pump storage, whatever it is, it doesn't matter. It's future-proof to whatever technology comes out in the market. You can do multiple things with the one system, like I said earlier, and the equipment is versatile enough to incorporate new forms of equipment 10 years down the road, 15 years down the road. Overall, the biggest driver for the private market is the savings for the operating costs. So we've taken a system to compare against our system, and over 20 years, you can realize 40% savings compared to a typical battery system. So we do that by getting more energy out of every single battery cell, and that's part of that BMS component of our software. Also, since we monitor down to the cell level, we can know exactly where problems are going to happen to predict or that have already happened. And we can categorize those as being very urgent and needing immediate service, or something that can wait until a regular maintenance event. So if you have a system that's deployed way out, we can look at the system from Northville or wherever base may be, and make that decision to send someone out to fix it or not. Also, we have 100% uptime because we go down to that cell level. We have a lot of redundancy. So part of your system will always be working no matter what, pretty much. There's always special circumstances, but. So kind of to focus on military capabilities and where our system might come in. Batteries are kind of, one analogy for batteries is it's like water. You have electricity is like water, and you can't manage electricity without buckets. So buckets are kind of like batteries. So that is in the case of microgrids. If you have a bunch of generators or some PV or some wind, you can basically store that energy in the batteries to be used on demand. Also, it's energy security. If there's a utility that you're going to hook up to, it's much more secure to generate your own source of electricity versus relying on something that might be controlled by a third party. Also, like I was saying earlier, we have the 100% uptime, unless someone were to bulldoze over the system completely. As far as deploying our projects, you can actually have it shipped in full-size containers for like a site, or it can all be shipped modularly. So, for instance, it's built to where you could take it down to someone's basement and completely assemble it from the floor up. It doesn't require any special training. It doesn't require any special parts. It's very plug and play. And so one other logistic advantage is you get the more energy out of less storage. So instead of having to have all these extra fuel costs or extra costs to buy more batteries that you're not actually going to use, we can take whatever resource you have or give you less resources to accomplish the same thing. So for instance, a typical battery, you can only take it down to 50% depth of discharge. So you're actually only using half the capacity. With our software, you can actually take it down to 80%. So you're basically getting more energy out of less batteries. Like I was saying earlier, it doesn't require any special tools or training to actually assemble our systems. So pretty much anybody can put it together if they got a screwdriver. So there's no special personnel that you have to deploy for assembly or for servicing. Also, it has minimal failure points, and anywhere that it might fail, it has a sensor there and data to actually monitor what's going on if in case there is a failure. And that monitoring system will alert you to know where the failure is and if it needs to be fixed. So that's pretty much it. If you have any questions, I'm more than welcome to ask away. Yeah. So like the Tesla home battery versus maybe one of our residential systems. Theirs is kind of like what I was saying, where you have one big box of batteries and it does one thing. So for instance, theirs is for backup power only, or it's for only integrating with the solar PV array. Ours, you can actually get revenue streams from the grid for participating in certain programs they may have, as well as providing backup power and also interacting with your solar. So basically, it manages the batteries to act different ways, as well as get more energy out of the batteries that are in the system.
Okay, I'm going to ask, it's going to sound like a challenging question because we've put in a number of solutions, and Ross, I'm sure you have, and Dan has. and always advertised as plug and play, simple
Yeah,
to
yeah.
use. And then we get it out in front of the warfighter, and so the complexity of connecting a storage and management system to a generator or to renewable power. I mean, is it truly plug and play?
Right.
And I can interface with commercial generators, military generators, in your thought, or?
Yeah, yeah. I mean, for instance, like I come from the solar industry, and I have personally installed multiple battery backup systems, and they call it plug and play, but it's 15 different components that you have to program and make them talk to each other. This is truly one box, has 4 ports, 2 DC, 2 AC. You literally just wire it up, and that's it. But to whatever inverter you're going to be using, it can either come with the inverter or you can interface it with a different inverter if you'd like. But it's very like constructs.
Right. And then a follow-up with Ross sitting there is your microgrid program, the Spiders, are you adding storage as a component to the microgrid? Because the Army has done a lot with microgrids, except they have not added the storage components.
Go for it.
So what we've observed in Spiders, it's 3 phases. First phase was a Joint Base Pearl Hickam. Second, and by the way, no relation to Spider 9. Spider stands for Smart Power Infrastructure Demonstration for Energy Reliability and Security. First phase was a Joint Base Pearl Hickam. Second phase at Fort Carson, Colorado. Third phase at Camp Smith, Hawaii. What we have observed is that, at least on a microgrid scale, the need for backup battery storage is not what we thought it would be going into it. First phase, we were going to use a flow battery. Contracting with the Air Force that was providing the flow battery didn't match up. Turned out we didn't need it. The generators, the smart microgrid control system, and a simple UPS was reactive enough to handle the variability in solar. Phase 2, we were going to use vehicle to grid as our storage mechanism, and it turns out that once again it was never used for stability of the variability of the solar, 1 megawatt of solar in that case, as much as it was for the volt-var stability of the entire base grid. And in phase 3, we've got a little bit of energy storage, but not much. It's called an ISOM, and I forget what it stands for.
Right, but the concept of a spinning reserve. So if I really want the microgrid, to provide on-demand power and not excess. So right now, if I have to run 2 generators, I'm still producing more power than I'm consuming because of that spinning reserve that's necessary. But if I had a storage capacity, I truly could do on-demand power and not burn more fuel than I need to. Am I incorrect?
Your statement is correct, but I think you're overselling the need for a spinning reserve. In a microgrid setting, what we have seen is that, okay, say you've got 2 generators at 725 kW. The load varies between 1 megawatt to 1.2 megawatts, right? You're going to use both generators that whole time. It's not like you can turn one of those off. If it gets up to 90% capacity, then you're going to have enough time to add in a 3rd generator and have the load equivalently distributed between those 3 generators that are microgridded together. Instead of having a spinning reserve, you bring up that 3rd generator as it approaches the point where you think you'll need a 3rd generator, and then distribute the load accordingly. Rod, is that your understanding of how it works?
The ISOMs, the Integrated Storage Inverter Modules, ISOM, will in fact provide a buffer if there was a large transient. Exactly.
A big spike, yes.
Right. So
Right.
they will provide you. Right.
You need some, like in phase 1 we had the UPS. In phase 3 we've got ISOM. In phase 2 we had the vehicle to grid, but the amount of storage required at a microgrid scale is not what we thought it would be going into it. No offense.
No, none taken.
Yeah. So we put in a number of different off-grid systems in various places. And I always find it kind of interesting when you take a look at, oh, we've got a mature technology, we've got a mature technology. And generally what they're talking about is somehow making solar panels cheaper or something. And the truth of the matter is the solar panels and that technology is relatively mature. The problem is, that we've experienced is it's not the cost of the solar panels that kills you, it's the rest of the system. It's the inverters, it's the controllers, it's the battery system. For a relatively small building, 20 by 32, using the DOE model for backup energy storage in the middle latitudes of the U.S., it's like $30,000 worth of batteries to make an off-grid system. Plus, there's about another $12,000 worth of inverters and controllers and that sort of thing. So if you're amortizing it for a structure over 20 years, it happens to turn out that you actually break even only because in 20 years you're going to have to replace most of those pieces. So you save the money over 20 years that pays off the system in 20 years, and then you immediately have to replace it. From what I was trying to understand from your presentation, you sort of implied that you can integrate the pieces from the inverter piece back all the way to the batteries and then reduce the number of batteries that I have to pay for, because that's really what kills you. $30,000 worth of batteries for a small building is it makes no sense. So is there is that, am I right? Is it,
Yeah,
I can
totally.
come and show up with a couple of wires off of my solar panels, you tell me I wanted it 240 or I wanted it 300,
Totally.
and I'll plug in that DC to your system, and I don't need to worry about inverters, controllers, or backup batteries. It's all built in.
Right, so that would be like our product for that small building. It'd be the Spider Vault, and included in a NEMA 3R enclosure is the inverter, the batteries, and the controls all together. All you do is plug in the PV array, a backup generator if you're going to have it, and your load. That's it. And all of that will run you less than $30,000. And that would be more than enough storage for that size of building, even. And you can scale that down to be lower or higher. That same box, you can put in more blocks of batteries if you wanted, or take them out.
Yeah, well, that's a great point, which brings up another question. When you start taking a look at billets versus dining facilities, that sort of thing, dining facilities eating power all day long. Tactical operations centers kind of go up and down. They have a little bit more during the day and goes down a bit at night. Billets, depending on, let's just for assumption's sake, billets tend to be a little power in the evening and no power during most of the day, other than keeping the air temperature controlled to a reasonable level so you don't start getting mold and things on the inside. But they all have roofs, so you can put lots of solar panels out there. So generally your solar field gets relatively large. It's managing the power subsequent to generating the solar panel, the sourcing field, between multiple buildings. It's a bit of the smart grid concept, but you may be able to do that by integrating all of those panels in one system. Does yours allow the expandability? So I can add more solar panels and you'll be able to manage between multiple buildings.
Correct. So, like for instance, what you're talking about is generation versus load mismatch. So solar day, you're going to peak at noon and you have this nice bell curve, versus your load, it might be a little in the morning, then a lot at night. So basically the storage will store that curve, that extra energy that's produced, to discharge whenever you need it on demand. If you have it set up, say, into a like some kind of load center for your loads, the OSC, the software, can actually control when that stored energy can be discharged, as well as predict what's going to happen based on previous history of the solar, how it's acting in the day. So if you're going to have a week of bad weather and you're not going to be getting as much production or as much stored energy into the batteries, it can basically alert to say, you're going to run out of power at this time if you don't get power from somewhere else. And that can do it on a site level or just on the single building level.
Okay, one more question before we let you go. So working, and this is to both Jill and Jordan, is how much access have you had to the military to understanding their operational challenges? I mean, you've shown a great slide, and we all kind of connect to that, but have you had access under this program?
Most of our customer discovery has been with the utility and with local solar EPCs. And so those solar EPCs are actually the ones that are installing like the PV systems on the military bases. That's been kind of our third removed connection to the military, yeah. But,
Oh, this one is on. Okay. So that's a interesting question. We actually work with our companies very closely to determine who their key customers and what their path to market is. So for a company like Spider 9, where they really want to focus on the utility, we provide a lot of access to the utility. We also can provide a lot of access to the military if that's of interest to do some customer discovery around, or if they see that as a key customer. And we have kickoff weeks for each track of our program where all the companies come together for a week and we introduce them to stakeholders across the entire ecosystem. So during that week, they definitely meet a lot of folks from DoD, which includes PACOM and the different bases.
Thank you.